Okay. Well, what we're going to be talking today, I'm going to start off with like a quick refresher on all the additive law of exponents stuff, because this is another section where being good with exponents really matters. And specifically where being efficient and accurate with exponents really makes a big difference. So just some quick refreshers, additive law of exponents wise. If I have something like 3 squared times 3 to the 5th, what our additive law of exponents says is if I'm multiplying, good morning, if I'm multiplying two things with the same base, then I can add those exponents together. And back somewhere in the first week of class, oh, sorry, my phone's making noise, not my intent. So back in the first week of class, I talked a little bit about the additive law of exponents. And we did some things like, let's say I have 5 to the 3rd times 5 to the -2. Well, in terms of those exponents, if I use the additive law, I'm multiplying two things with the same base. So I know that I can add those exponents up. And 5 to the 1st is just equal to 5. We also talked, oh, questions already.
You read it to instead of the 3.
Cool. How about that? Good call. 3 to the 7th, yes. And there are a couple of special things that happen with our additive law of exponents, and one of those, just to recap, if I had 2 squared times 2 to the -2, that's a lot of 2's. That would be 2 raised to the 2 plus -2, or 2 to the 0. And we talked about how that negative exponent we can actually think of as saying 1 divided by 2 squared. And that 2 to the 0 piece is equal to 1. And any number raised to the 0 power is equal to 1. And I will put a link back to that first day where we were talking through all the additive law of exponent stuff in case people want more of a refresher than that. But what we're doing in chapter 4 is all of these skills that we have with exponents, we're now going to apply them to variables, not just numbers. But I want to get just a little bit more practice specifically with negative exponents, because that's a place where people tend to make more mistakes. So if I write 5 raised to the -3rd power, and again, I made my pitch before about handwriting matters and sort of the font size of your handwriting matters. It's important that somehow you have a mechanism to make sure that you know that says 5 with an exponent of -3, not 5 minus 3 when you're going quickly through your paper. Sorry. We have 2 ways that or at least 2 ways that we can think about this. One common thing that I hear is that the negative basically means that it's on the wrong side of a fraction bar. So in this case, because I had a negative exponent and that 5 was just kind of hanging out by itself, being on the wrong side of the fraction bar meant that I could move it to the denominator. If I had something like 1 over 3 to the 4th power, I also could choose to rewrite this as saying 3 to the negative fourth. Now going back and forth between these two notations is going to be useful as sort of a pre-calculus and calculus tool. It's also going to be useful in terms of just checking your work in the back of the book. But if the instructions say to write your final answer with positive exponents, then this notation or this notation, right, is the right one to do, even though these are algebraically equivalent. And I do have the chat open in case people have questions on Zoom. Not seeing much in the chat at the moment. So let's dive into having some fun. So if I had something and my instructions here are going to be to simplify to lowest terms with only positive exponents. There are lots of different options for how we want to think about this. So I'm going to do this two different ways. The first way is I'm going to use our exponent laws to say that I'm dividing two things with the same base, which means I can subtract the exponents. So this would be equivalent to 5 to the 3 minus 7, or 5 to the negative fourth. And then when I'm done, because I need to write this with only positive exponents, I would need to move that as 1 over 5 to the fourth. I will tell you that is not what happens in my head. In my head, when I see this problem, what I actually do is really similar to how I simplify fractions with numbers, which is I'm going to take the bottom and I'm actually going to write that as the product of 5 to the third times 5 to the fourth. Because to me, now that 5 to the third over 5 to the third is a 1, and I get to 1 over 5 to the fourth. I prefer to have fewer rules and just a few kind of go-to things that I do with my algebra. But I totally respect that some folks really like to have a set of rules to follow. And that works too. Either way, we're getting to the same place. Yeah, question.
I can understand how you got how you set it up, or comes up the other two.
My second version? Yeah. So when I see 5 to the 7th, I know that that means 5 times 5 times 5 times 5 times 5 times 5, 1, 2, 3, times 5. And technically, that numerator of 5 to the third means that I had 5 times 5 times 5. So in my head, what I choose to do is take that 5 to the 7th and break it up into two groups. One group that has 3 of those 5s and one group that has 4 of them. Because I know that the group with 3 of the 5s is going to cancel out with the group that has 3 5s on top. Don't have to do it that way. Again, I'm just offering sort of alternative approaches if memorizing a bunch of rules hasn't worked out for you in the past. Let's do another one, or 12. Life always gets complicated when we throw more negative signs in the mix, but same rules. I'm not going to keep writing it, but simplify to lowest terms, make sure we've got positive exponents. Just a note on notation for a second, and we've probably talked about this before, but if I have -3 squared, the way that this is currently written, this means that I'm going to deal with that exponent first. This is -3 squared or -9. If I want it to mean something else, I would need to put parentheses around that -3. So if I have parentheses around the -3, this means that I have -3 times -3, which is equal to +9. So just something to kind of look out for when it's not exactly an exponent rule, but it is a notation thing that we should be aware of. Okay. Back to more simplifying stuff. So if I had 4 squared times 5 to the 7th over 4 to the 5th times 5 cubed. We have choices again for how to get through this problem. One of the options that we have that I would probably suggest is to really think about this by grouping the 4s and then grouping the 5s. Do you have to rewrite it like this to do that? Absolutely not. Just offering options. So if we go with straight using our exponent laws, I'm going to subtract my exponents on the 4. So I'd have 4 to the 2 minus 5 times. And then with my 5s, I'd have 5 to the 7 minus 3. Well, if I simplify each of those, that's 4 to the -3rd times 5 to the +4th power, which is a simplified form, but it contains negative exponents. So we would want to rewrite this as 5 to the 4th divided by 4 to the 3rd. Question. So this is equivalent to 1 over 4 to the 3rd times 5 to the 4th. But I'm putting them together. Just like if I had, if I had something like 1/2 times 5, well, I could leave it as 1/2 times 5. I would write that as 5 halves. And this would be the more simplified form. Yeah. Okay. All of these same rules with how we deal with fractions and how we deal with exponents, they apply whether I'm talking about constants where I know their values, or if I have some sort of variable where I'm not sure what the value is yet. So here, if I'm going to put this in lowest terms and have only positive exponents, I am definitely going to separately think about the numbers part and the variable part. this time simplifying the numbers doesn't involve dealing with exponents. It just involves remembering all of our fun rules about fractions. So I can take that 10 and rewrite it as 5 times 2. So that my 5 over 5 becomes a 1. And if I look at the x's, I can either think about that as x raised to the 3 minus 5, or I can break apart that x to the 5th and think about it as the group of x to the 3rd times the group of x squared. Which once again, I've got that x cubed over x cubed, which equals 1. So I would have 1/2 times 1 over x squared, but the most simplified way to write that would be 1 over 2x squared. I will also say, if you go straight from here to here and show no intermediate steps, that is completely fine with me. If you're good with exponents and you're good with fractions and you see this as this, go for it. I don't need to see any work. Let's say I've got y to the 3rd, x to the 4th over 3y squared, x squared. I've got numbers, I've got y variables, and I've got x variables. So when I look at this, I'm going to think about pairing each thing up on its own. So numbers wise, there's an invisible 1 on the top. And then I've got y to the 3rd over y squared. And I've got x to the 4th over x squared. And if I simplify each of those, well, the 1/3, there's nothing to reduce. On my y's, if I were to write this out on top, that y to the 3rd is the same as y times y times y, and that y squared is a y times y. So you can think about it as sort of 2 sets of y's canceling out, if you like. And then on my x terms, and I know I'm showing this like lots of different ways, just trying to give us lots of options, which can be frustrating in math, but it is also the reality. Pausing for a second in case that generated any questions. Okay. So one of our other exponent rules that maybe we talked about before as a rule, maybe we didn't, I don't know. I actually don't remember. If I had something like 5 to the 3rd to the 4th, so I have powers raised to powers. This says I have something to the 4th, which means that something would get multiplied by itself 4 times. And the something that I have in there is 5 to the 3rd. So all told, if I wrote all those out, that's 3 5s and another 3 5s and another 3 5s and another 3 5s. That's the same as 5 to the 3 times 4, or 5 to the 12th. In our continuing saga of dumb things our brains do, if I wrote something like 2x cubed to the 5th power, the number one wrong answer that I see written down is to write that as 2x to the 15th. The problem is that that number is inside the parentheses and that number is getting an exponent also. So what this actually is 2 to the 5th times x to the 15th. If you wanted to multiply out 2 to the 5th, that's one that we could actually make a number. But that is like the number one thing that people do wrong with the exponent stuff, is treating the numbers like it's something completely different. So I'm going to make a messier one here. And let's say I've got 3x cubed y to the negative 2 squared. Sure, we'll just go with that at first. So I'm looking for the same instructions. We're going to simplify to lowest terms, and we're going to make sure that our final answer has only positive exponents. Well, this whole thing squared fundamentally means that I've got all of that stuff in parentheses times all of that stuff in parentheses again. You do not have to write this out, but if it helps you to write it out, go for it. One way that we think about this is because it's all multiplication inside of the parentheses. That's a place where I can sort of distribute that exponent through. So this would look like 3 squared and x cubed squared and y to the negative 2 squared. And if we clean each of those up, 3 squared is going to be 9. X cubed squared, powers raised to powers, I'm going to multiply that. So I'll have x to the 6th, and then powers raised to powers, that would give me a y to the negative 4th. I'm almost done, but we want to make sure that we write our answer without negative exponents. So I'm going to need to rewrite that to say 9x to the 6th over y to the 4th. Questions, answers, having some fun. Question. Yes.
So the second one is where
This one? So this whole thing is squared.
oh,
Yep.
okay.
Yeah, so we're kind of distributing that power into each piece. Yeah. Okay. 4x to the 6th, y whole thing to the negative 1 over 8 to the negative 2 squared y to the negative 3. Okay. I made a nice messy one. Do you all want to try this one on your own? Yeah, why not? Try to simplify that thing on your own. Good times. I know it looks really gross. Do we want a little bit more time to play with it on your own? Or should we fight through this thing together? No responses. I'm gonna take that to mean we should do this thing together. Okay. We have all kinds of choices for how we go about this, but I'm gonna start by attacking the exponents and parentheses part. Just thinking about our order of operations, right? Parentheses, exponents, multiplication, addition, multiplication, division, addition, subtraction. So if I think about the top, I have only multiplication inside of those parentheses, which means the exponent can get distributed in. So in the numerator, that's going to look like 4 to the negative 1, x to the 6 to the negative 1, and y to the negative 1. Oops. There are other ways to go about this. I'm just choosing a path. Now, we still have path choice, right? One option is that idea of thinking that a negative exponent means that this piece is on the wrong side of my fraction bar, right? And if I move it to the other side of my fraction bar, we can write it as a positive exponent. So if I take that approach, then that 4 to the negative 1 can become a 4 to the positive 1 in the denominator. And that 8 to the negative 2 can become an 8 to the positive 2 in the numerator. Powers raised to powers means that I would multiply this out. So that x to the negative 6, if I put it in the denominator, it'll become x to the positive 6. I still have that x squared down there. There's nothing wrong with its exponent. Now, if I look at the y's, that y to the negative 1 in the numerator tells me that I can put it in the denominator with a positive exponent. And the y to negative 3 in the denominator, I can put in the numerator with a positive exponent. Now, I know I've left a lot of space between the 8 squared and the y, but I was kind of trying to line things up together. So 8 squared, I can make it smaller or bigger, but 8 squared is 64, so I'm just going for it. So if I pair up the numbers, and then looking at the x's, if I pair these up, x to the 6th times x squared would be x to the 8th, because I'm adding those exponents. And on the y's, I would end up with y squared on the top. There are lots of correct ways to do this and lots of correct ways to write this. But it is not in the simplest or lowest terms form. 64 divided by 4. Anyone got a number for me? Cool, it's 16. So I got 16. So on the top, I've got 16y squared, and in the denominator, I'd have x to the 8th. That is not the only option for how to handle this. It is one option for how to handle this. Good times? Yeah, question.
So since you have the negatives right there, the 4 to the negative, or 8 to the negative negative power,
Mhm.
would you just flip them, right, to make a positive in a sense?
Yep. Yeah, so for the sake of those on Zoom who maybe didn't hear that, because the 4 to the -1 and 8 to the -1 have negative exponents, to make those exponents positive, we're like flipping them to the other side of our giant old division bar. Yeah. Dun, dun, dun. Okay. The exponent stuff, it's just something that's going to continue with us for the rest of our mathy lives. It's going to show up in lots of different places that we're doing math. So if someone really likes rules, let's just do a quick recap from like a rules perspective. So if I have x to the a times x to the b, then our additive law of exponents says that's x to the a plus b. If I have x to the a divided by x to the b, that's the same as x to the a minus b. If I have x to the -a, that's the same as 1 over x to the a. And similarly, if I have 1 over x to the -b, that's the same as x to the positive b. Then we have a couple of things that are just sort of facts we ought to memorize. X to the 1 is just x. We don't write the exponent. That's mostly a notation thing. On the first, I think it was like the very first day of class, we did additive law of exponents to show that if I have any number raised to the 0 power, that's equal to 1. There's an exception, and that's when a is equal to 0. And we will save that for a calculus discussion. So 0 to the 0, we will explore in calculus. Interesting stuff happens with 0 to the 0. I'm kind of going to switch gears just a little bit here to talk about monomials. Actually, no one really cares about that word, but to talk about where we're headed next, which is most of the time we're not dealing with a single number or a single like variable raised to a power. We're often dealing with things that look like 3x squared plus 4xy minus 12xy squared. Each of these terms is called a monomial. Mono meaning one, like it's one thing that's glued together, which each monomial would be comprised of a number potentially that we call the coefficient. And then we might have variables that are raised to powers. So in this case, we had an x squared. So I'd have a variable and a power. Now, even if we have more than one variable, it's still a monomial. We talk about, or we could talk about the degree of a monomial being the total sum of the powers. That's all vocabulary that we don't really need to worry about right now. What is important is that there's a phrase that comes up a lot, which is like terms or similar terms. And in the context of monomials, what that means is that the coefficients could be different, but the variables and the powers have to match. For example, if I had 4xy and negative 3xy, these are like terms because they both have an x raised to the first power and a y raised to the first power. If I had 3x squared and 17x squared, these are like terms because they both have an x, and in both terms it's raised to the second power. If I had 5x cubed y to the negative fourth, and I had x cubed y to the negative fourth, these are also like terms or similar terms because the variables are raised to the same powers. But if I had 4x and 3y, these are not like terms. Or if I had 3x and 12x squared, these are also not like terms. Even though they have the same variable, those variables are not raised to the same power. Now, the reason that that's important is that when we are multiplying two things together, we kind of don't care if the things look the same, right? We've had some examples today of other problems where we had x's and y's and numbers jumbled up together. And when we're doing multiplication and division, that's fine. But when we're having addition or subtraction, we can only add or subtract things that are like terms. Now, the analogy here is if I go back to thinking about fractions, if I have 5/12, I can add that to 7/12. Because essentially these two are like terms. They're both something with 12ths. But if I had 3/12, I said 3, I wrote a 2, I'm just rolling with the 2. If I had 2/12 plus 3/5, I would have to do some work first. I would need a common denominator. So when we're thinking about monomials, if I had like a whole bunch of monomials here, I had like 3x squared plus 4x minus 6x plus 2 minus 10x squared. Some of these terms I can combine together because they have like terms, and others I can't yet. We'd have to do something. So if I go to simplify this or to write this in its most simplified form, what that would mean is to combine the terms that are similar. So I'm going to start with the x squareds. I have a 3x squared and a negative 10x squared. Those two pieces I can put together. 3 of the x squareds minus 10 of the x squareds leaves me with negative 7 of the x squareds. Then I can look at my x terms, and I've got 4x and negative 6x. So if I put those together, I'm going to end up with, that is a little bit light. I'm going to end up with negative 2x. And then my last piece here, I've got that plus 2. And then we've taken care of each of the terms to combine those into one most simplified expression. We can do the same thing even if I've got more than one variable in the mix. So let's say that I had a cubed plus 2a squared b minus ab squared plus 4ba squared minus 5b squared a plus 7. So I've got a jumble of monomials here. Oh, by the way, when we put them together, it becomes a polynomial because I have more than one piece here. But if we go to pull these together, and I'm thinking about like terms, one of the things to keep in mind is that because the order that we multiply numbers in doesn't matter, some of these things are like terms, even if they don't immediately pop out as being like terms. So two things have like terms if they've got the variables raised to the same exponents. So I'll start with that a cubed term. We don't have any other pieces that are raised to an exponent of 3. So there's nothing I can combine together with that. I'll just keep the a cubed by itself. Now that 2a squared b, I can combine with anything else that's got an a squared times a b. And we have another piece with an a squared times b. It was just written in a different order. But the order of multiplication doesn't matter. So when I put these two together, I've got 6 a squared b. Next up, if I look at that negative ab squared, and again, the order that we've multiplied things in doesn't matter. That is a like term to the negative 5b squared a, because they both have an a raised to the first power and a b raised to the second power. Putting those together, I'm looking at negative 6b squared a. And then we've got that lonely 7 hanging off the end. And that's the best we can do. It is tempting to look at those two terms in the middle and have your brain want to cancel them out. I had positive 6 of a thing, I had negative 6 of a thing. The issue is they're not like terms because the exponents on the a's and b's are not the same. So we would have to quit there. We've got about 5 minutes left, and I just want to add a couple of additional geometry formulas to the mix from what we did last time. There are some word problems in this chapter where we might need some additional geometry formulas. So we will take a pause from fun with exponents. And so there are lots of different names for this shape. I am going to be boring and say it's a box. Technically it's a parallelepiped, or I don't know, there are probably other names for this, but it's a 3-dimensional object that has a length, a width, and a height. And for this box, we would calculate the volume, and this is actually true for lots of solids. The volume is the area of the base times the height. And since the base of this object is a rectangle, the area of this would look like the length times the width. That would be the area of the base. And then I would multiply that by the height, or length times width times height. When we're talking about volume, if we need to think units, then if the length, the width, and the height each had units of inches, then this would have units of inches times inches times inches, or inches cubed. So in general, my units for volume would be things like centimeters cubed, or inches cubed, or feet cubed. But it's some measure of length cubed. I guess I can add in meters cubed. Another three-dimensional shape, and I'm just going to squeeze it in here, but another three-dimensional shape that we sometimes have to deal with is a sphere. My drawing skills are not wonderful, but you can imagine that that's a sphere. And the volume of a sphere is 4/3 pi times the radius cubed. Because we would measure the radius in things like centimeters or inches or feet or meters, the units are the same for any kind of volume. It's some sort of distance measurement cubed. I think those are the only two formulas that you might need for working through problems in this chapter in terms of like geometry-ish formulas. Both of these you should memorize. They're going to come up in pre-calc. They're going to come up in calculus. Just throw that in the back of your head. I got 1 minute left. Anyone have a random question for me? Cool. Have a lovely rest of your day. It's getting brighter outside. It is no longer looking quite as gloomy. You are very welcome. If anyone hasn't had a chance to submit quiz 3 yet this morning, please do so I can get those graded. Bye.